Alright, welcome back. So in the last video, we experimented with calculating the slope of the best fit line. We called that slope b. We learned that the slope of the best fit line will not in general be zero. Even random data would have a trend, usually a small trend, but sometimes a not so small trend. Now before we move on, I'm going to let you in on why the slope of the best fit line is called b. The best fit line was created by the data itself. We didn't learn the actual equations involved, but the basic idea is that you use the numbers themselves to come up with a best fit line, and the slope of that line is b. But presumably there is some real trend in the data. If we had perfect information about the nature of the temperatures at the station with respect to time, we would find that there is some real trend. Let's call that beta. Beta is the real trend if we had perfect information. Our b, the slope of the best fit line, is not beta. Our b is an estimator of beta. It is a good estimator of beta. In fact, it can be proven that it is the best estimator of beta, but it is not exactly the same thing as beta. In our experiments with the random numbers, beta would be 0. In a perfect world with perfect information, the real trend in random numbers is 0. However, as we saw, the short, imperfect sets of random numbers could have a short-term trend b that was non-zero. In fact, in general, they did have a non-zero value of b. Because beta is our real trend, and beta is the Greek letter for b, we use b as our estimator of beta. This is just a standard way that statisticians use their symbols. They use the Greek letter for the real phenomenon, which they don't actually know, and they use the corresponding letter of the alphabet for the imperfect estimator. Now let's think about what we learned in the last video. We learned that in order to be considered statistically significant, our results needed to have a slope b that was outside the range that was likely to occur just by random chance. I mean, no matter what, there will be some small trend in the data. After all, even random numbers showed some small trends, right? The central question is the trend that we are seeing in the data big enough that it was unlikely to have happened just by chance, and therefore reveals something interesting about the data? Let's design a logical test to see if our value for b, the slope of the best fit line, is far enough from 0 that it is a significant result. The way I see it, we could say that either the trend in the data is being created by values that don't really have a trend, or the trend in the data is being created by values that do have a trend. Therefore, I would say that we have two hypotheses, two ideas that can be tested. The null hypothesis is that these data don't really have a trend. We use the symbol H0 for a null hypothesis. Sure, b is not exactly 0, but in this case we are hypothesizing that beta, the real trend in the data, is 0. H0 is that beta equals 0. The alternative hypothesis is that these data really do have a trend. We use the symbol HA for the alternative hypothesis. Again, my calculated value of b is non-zero, but in this case we are hypothesizing that it is far enough from 0 that beta, the real trend in the real world, is non-zero too. HA is that beta does not equal 0. The null hypothesis H0 and the alternative hypothesis HA have been designed in this case to be really clever. For example, notice that they account for every possibility with regard to beta. Either beta is equal to 0 or beta is not equal to 0. There's nothing else it can be. Also notice that H0 and HA are mutually exclusive. If H0 is true, HA is false. That is, if beta is equal to 0, beta can't also be non-zero, right? Similarly, if HA is true, then H0 is false. This is a powerful way to set up a problem in science, and has a name. It's called hypothesis testing, and hypothesis testing created the modern world. Every bit of science and technology around you was created using scientific information that was tested and evaluated using these kinds of hypothesis tests. Every medicine was evaluated for safety by applying tests like these to see if the people who took the medicine had more side effects than the people who took a placebo. Every safety feature on your car was scrutinized using such tests, determining whether or not the feature made the car safer. How we grow, transport, handle, and cook food. How we improve fuel efficiency in cars. how we optimize data networks to improve speeds. All of these features of modern society were subjected to these kinds of hypothesis tests to make sure that the scientists and the engineers understood what the data were telling them. These kinds of hypothesis tests work. They work well. They make sure the scientists have good reason to believe what they believe. They don't lie. The hypothesis tests don't have a political agenda or anything like that. I'm telling you this because I want you to understand something very important. These tests, you can believe them. If the hypothesis tests say that a temperature at a station is increasing, then the data say the temperature is increasing. Case closed. Well, sort of. The test isn't telling us why the temperature is increasing. That would require different kinds of scientific experiments and different kinds of statistical tests. But the question of whether or not the temperature at the station is increasing will have been answered. No bull about scientific hoaxes or biases or whatever. The tests work, just like they worked in the experiments that created new medicines or safety features on your car or improved agricultural chemicals or whatever. Science works. It works when we're talking about new medicines or gadgets or whatever, and it works when we're talking about climate change. So let's get back to our two hypotheses. We have a set of temperature data from a weather station. We wrote two hypotheses about these data. The null hypothesis is that the data don't really have a trend. The alternative hypothesis is that the data do have a trend. Because the two hypotheses are mutually exclusive and include all of the possibilities, if we could just rule out one of the two hypotheses, we would know what the data mean. We would know whether or not the data are showing a trend. Let's work on the null hypothesis, the one that suggests that the data don't really have a trend and that beta is really zero. Sure, when I computed b, the slope of the best fit line, it wasn't exactly zero, but h0 is saying that it should be close to zero most of the time, just like the slope of the best fit line was usually close to zero for the list of random numbers that we created in the last video. In other words, we would expect b to be a lot like the slopes of the best fit lines that we came up with for random numbers. Well, that's something we can test. Remember, the slopes of the best fit lines of lists of random numbers looked like a type of bell curve, with most of the slopes being close to zero, and a few of the slopes being surprisingly far from zero. Let's compare the value of b that we got from the data to that bell curve distribution. If the value of b is near the middle of the distribution, well, lots of lists of random numbers resulted in trend lines that had slopes that looked like that. Since even random numbers had trends that were that big, this result doesn't seem all that different from the results that we would expect if the data were like the lists of random numbers and didn't really have a trend at all. It looks like h0, the null hypothesis that the data don't really have a trend in them, is probably true, which means that HA, the alternative hypothesis that the data really do have a trend in them, is false. We accept the idea that the data don't have a trend in them. On the other hand, suppose that our value of b is way out in the tail of the bell curve distribution of trends that we got based on lists of random numbers. Sure, maybe, once in a while lists of random numbers did actually show a trend that was as big as what was being seen in the data, but it only happened very, very rarely. This b, this trend that we computed based on the data, really isn't acting very much like a trend we would see in lists of random numbers that don't really have a trend at all. This b is big enough that it is really improbable that this value could have happened in lists of trendless random numbers. It looks like h0, the null hypothesis that the data don't really have a trend in them, is probably false, since our list of data had a value of b that was really improbable when compared to the distribution of trends seen in trendless lists of random numbers. If h0 is false, then ha has to be true. We reject the idea that the value of beta is zero, we reject h0, and we accept the alternative hypothesis that the data do show a trend. As it happens, there are tests to figure out the probability that the value of b that you computed could have been based on the data could have been created just by a list of random numbers by chance. Again, the test is pretty complicated, and there are differences between how Google Spreadsheets, Excel, and other statistical tools do it. Having you struggle with the tools themselves is not exactly the point of this activity. Rather, once again, we've created spreadsheet templates for you. Under the Incoming tab, in the Tools for ATS 114 folder, you'll find a spreadsheet called Testing a Trend Template. Load that, and then save it under a different name in your own account. We'll walk you through how to do all that on the next page in blue line. Once you have that spreadsheet, you'll just cut and paste data from other spreadsheets into the appropriate columns, and the template will go ahead and compute the necessary statistics for you. You'll find that one of those statistics is the probability that this trend happened by chance. Based on that probability, we can go back to our two hypotheses and figure out what that means. Remember, our null hypothesis is H0, beta equals 0, and our alternative hypothesis is HA, beta does not equal 0. These two hypotheses are mutually exclusive and include all of the possibilities. Exactly one of these hypotheses is true, the other has to be false. Well, our statistical test of the significance of the value of the slope of the best fit line will give us the probability that the value of B that we got could have been created just by a string of random numbers, rather than by a data series based on real observations with a real trend. In this case that I just worked out, that probability was pretty small. It came out to 0.0036, or a 0.036% chance that the value of B that big could have been the result of a string of random numbers. Is that low? Yeah, that's pretty low. It makes H0, our hypothesis that beta is 0, not very likely, right? I think we can safely say in this case that H0 is false, and since the null hypothesis and the alternative hypothesis are mutually exclusive and contain all the possibilities, if H0 is false, then H8 is apparently true. Therefore, in this case, we have used a statistical hypothesis test, and we have determined that apparently the trend in the data is non-zero. There is a trend in this data set. So now move on to the blue line quiz associated with this video and complete the activity. You'll be formulating a set of hypotheses and then testing those hypotheses using the spreadsheet template that we provide. When you complete the activity, you will know whether or not there is a trend in the data. You will know this in the sense that scientists know results when they conduct their research. You will have proven whether or not there is a temperature trend at a given station, at a given time of year, etc. I'm excited that you get a chance to try this for yourself as part of Creighton's Magis Core curriculum. If you have any trouble getting any of this to work, contact me or your TA.